Albatross-Inspired drone soars without flapping wings, biomimicry breakthrough. Imagine a drone that doesn't need engines, just the wind. A team of U.S. researchers is on a mission to mimic the albatross's effortless oceanic flights, turning nature's secrets into next-gen technology. UC Assistant Professor Same Elsa and his collaborators are developing drones that harness the same wind-powered technique these majestic birds use to glide for hours without flapping once. With a wingspan of over 11 feet, albatrosses have mastered the art of dynamic soaring, a strategy that could revolutionize how we think about unmanned aerial vehicles. But here's where it gets controversial. Can machines truly replicate the uncanny precision of a bird's flight path? ESA, who has secured a $700,000 grant from DARPA, admits the challenge is immense. Albatrosses solve an optimization problem so complex even advanced computers struggle to match, he says. These birds don't just fly, they calculate. By turning into the wind like a sailboat, they gain altitude, then convert that energy into speed by gliding forward. Near the water, they repeat the cycle, staying airborne for days. GPS tracking reveals they can cover hundreds of miles weekly, 20 times the Earth-Moon distance in a lifetime. The science behind this is fascinating. Albatrosses use their sensitive nose to adjust flight mid-air, a level of finesse that engineers are trying to replicate. In simulations, ESA's team found that even top-tier computers can't plan a better route in real time. A few seconds of data takes 100 seconds to process for a drone, but albatrosses do it instantly, he explains. This isn't just about efficiency, it's about elegance. The birds make it look natural, yet the math behind their flight is mind-blowing. The project's goal is to turn this biological marvel into a practical solution. By studying how albatrosses exploit wind patterns, researchers hope to design drones that can soar longer, consume less power, and operate autonomously. Nature has been refining flight for millions of years, ESA says. We're not just copying nature, we're learning from it. Of course, not everyone will agree. Can a machine truly match the adaptability of a living creature? Or will this technology only scratch the surface of what nature has already perfected? As ESA puts it, the future of drones might not be powered by batteries, but by the wisdom of the wind. What do you think? Share your thoughts in the comments below. Unlocking the secrets of albatross flight, engineering the future of drones. Imagine a drone that glides effortlessly across vast distances, powered not by batteries, but by the very winds that surround it. Sounds like science fiction? Not anymore. At the University of Cincinnati, aerospace engineering professor Same Issa is turning this vision into reality by studying the flight patterns of albatrosses, birds that have mastered the art of wind-powered travel for millennia. But here's where it gets controversial. Could nature's design outperform even the most advanced human-engineered systems? And if so, what does that mean for the future of drone technology? Let's dive into the science behind this groundbreaking work. Albatrosses, those majestic seabirds with wingspans stretching over 11 feet, are the ultimate long-distance travelers. They can soar for days without flapping their wings, covering hundreds of miles a week. But it's not just their size that makes them extraordinary. It's their ability to harness wind energy with near-perfect efficiency. ESA, supported by a $700,000 grant from DARPA, is decoding this natural phenomenon to create drones that adapt to wind conditions in real time. His project, rooted in biomimicry, aims to replicate the albatross's secret weapon, a technique called dynamic soaring. Dynamic soaring works like this. The birds alternate between climbing into stronger wind currents and diving to gain speed, extracting energy from the atmosphere itself. ESA's team has dubbed this process a natural extremum-seeking system, a term borrowed from control theory. Essentially, the birds, and the drones they inspire, constantly calculate the optimal angles of pitch, yaw, and roll to maximize efficiency. Think of it as aerial sailing, tacking into the wind to climb, then turning downwind to accelerate. At the peak of their arc, they skim just above the ocean's surface, before repeating the cycle, all without a single wing beat. But their wings aren't the only secret, ESA explains. Albatrosses have an almost supernatural ability to sense wind shifts through their highly sensitive nostrils. These aerial noses allow them to fine-tune their flight paths, ensuring they never waste energy. ESA's simulations reveal that the energy gained from wind currents nearly cancels out the energy lost during flight, creating a closed-loop system. They're solving an optimization problem that would baffle even the most advanced computers, he adds, and they do it in real time. So how does this translate to drones? ESA and his collaborators are developing algorithms that mimic this behavior. The challenge? Replicating the albatross's split-second decision-making. A few seconds of data can take 100 seconds to generate in a simulation, ESA notes. Yet the birds do it effortlessly. To achieve this, drones must constantly measure wind speed and direction, then adjust their angle of attack and roll in milliseconds. The goal? To turn winds from a liability into a power source. Project Albatross, the DARPA-backed initiative, brings together experts from academia, industry, and meteorology. The team is testing prototypes with UC's industry partners to quantify energy savings compared to traditional flight methods. Beyond drones, this research could deepen our understanding of bird flight itself. ESA believes dynamic soaring might be the first confirmed example of extremum-seeking behavior in nature, a hypothesis that could reshape how we model animal movement. But the implications go beyond efficiency. As UC Associate Dean Gautam Pillai points out, this work aligns with critical defense priorities, such as extending drone endurance in contested environments. ESA's research exemplifies how biomimicry is driving next-generation aerospace systems, Pillai says. For students, the project offers hands-on experience in a field where theory meets real-world impact. It's not just about equations, Pillai adds. It's about solving problems that matter. ESA's passion for flight is deeply personal. When asked to choose a superpower, flight or invisibility, he doesn't hesitate. Flying is fascinating. It's something we always yearn for because we can't do it. That longing, he argues, is why biomimicry holds such promise. Nature has been refining flight for millions of years. Now, engineers are learning from its blueprint. To take this gift from nature and make it available to humanity is engineering at its best, ESA says. Related stories. Drone Research Lab at UC Merced, chosen as new hub for system-wide policies. https://www.azorobotics, News ID. Commercial drones, the challenges facing the aerospace industry. Article azora.com/article ID. UC College of Nursing and CEAS to host UC Robotics Night. https://article ID 316. www.azorobotics, News ID 6469. And this is the part most people miss, the philosophical debate at the heart of this work. Should we rely on nature's designs, or is there value in forging our own path? Do you think biomimicry will dominate future engineering? Or will human ingenuity find better solutions? Share your thoughts below. Let's spark a conversation about the future of flight. Unlocking the secret to longer drone flight times with Albatross-Inspired tech. The flight technique known as dynamic soaring utilized by albatrosses may hold the key to significantly enhancing drone flight times by harnessing wind energy. In summary, researchers are drawing inspiration from the albatross to boost the efficiency of drones through dynamic soaring methods. A generous grant of $700,000 from DARPA is funding this initiative aimed at refining unmanned aerial vehicle UAV designs. The goal of the project is to transform the challenges posed by wind into beneficial opportunities for drones by emulating the flight patterns of albatrosses. This innovative approach could lead to longer drone flight times and lower energy usage, which would have significant implications across various sectors. In an exciting development that could revolutionize the realm of unmanned aerial vehicles, UAVs, researchers are looking to the natural world for guidance. Albatrosses, renowned for their impressive wingspans and their ability to glide effortlessly over vast stretches of ocean without the need for flapping, are providing valuable insights into the design of drones. Leading this pioneering effort is UC Assistant Professor Same Isa, who is supported by a substantial $700,000 grant from the Defense Advanced Research Projects Agency, DARPA. The aim is to replicate the bird's dynamic soaring techniques, which could dramatically enhance the flight duration and efficiency of drones, potentially reshaping the UAV industry. Understanding dynamic soaring. Dynamic soaring is an extraordinary flight method that enables albatrosses to cover extensive distances while expending minimal energy. This technique involves utilizing wind currents to gain both speed and altitude, allowing the bird to glide for hours without the need to flap its wings. Professor Issa and his research team have created a system that emulates this natural principle, referring to it as a natural extremum-seeking system. This system allows the bird to first turn into the wind to capture faster air currents, then glide forward, leveraging both gravity and wind to sustain its speed. As the albatross begins to slow down, it turns back into the wind, repeating the cycle to conserve energy. The researchers are optimistic that by applying this principle to drone technology, they can achieve similar levels of energy efficiency. This groundbreaking approach has the potential to extend the operational range and duration of UAVs, which is crucial for both commercial and military applications. Nature's Flight Insights. Professor Issa highlights the remarkable ability of albatrosses to utilize dynamic soaring for prolonged flights. Equipped with GPS trackers, these birds have been observed flying hundreds of miles each week. Over their lifetimes, they can cover distances equivalent to 20 times the journey from Earth to the Moon. One particularly intriguing aspect of their flight is their highly sensitive noses, which allow for precise adjustments during flight, something that even the most advanced computers struggle to replicate in real-time simulations. Issa notes, they are solving an optimization problem that is unbelievably complicated. The albatross's capacity to perform real-time calculations with remarkable accuracy is a critical feature that drones must replicate to achieve autonomous soaring. The challenge lies in accurately measuring fluctuating wind speeds and directions to determine the optimal angle of attack and adjust flight controls accordingly. Overcoming challenges and technological barriers. Traditionally, wind has posed a significant challenge for drones, but this project aims to turn that challenge into an advantage. By developing new flight control systems based on the techniques used by albatrosses, researchers hope to enable drones to adapt to changing wind conditions in real time. This endeavor requires intricate design work and collaboration with industry partners to evaluate the energy efficiency of this new method compared to conventional drone flight. Issa asserts, nature has been optimizing flight for millions of years, and by employing biomimicry, engineers can tap into this evolutionary advantage. The project aspires to integrate these natural efficiencies into UAV technology, pushing the limits of what is achievable in autonomous flight. This initiative not only showcases the potential of biomimicry in engineering, but also emphasizes the importance of interdisciplinary collaboration in addressing complex technological challenges. Future implications and directions. The ramifications of this research extend well beyond academic curiosity. If successful, this project could lead to UAVs that boast significantly longer flight times and reduced energy consumption. Such advancements would have profound implications for industries that rely on drone technology, ranging from agriculture to defense. By embracing designs inspired by nature, engineers can create drones that are more resilient and adaptable, capable of addressing a wide array of challenges. As the project continues to evolve, the potential for further innovation remains vast. Researchers are actively investigating how additional aspects of albatross flight can be incorporated into UAV design, with the goal of creating drones that not only mimic natural flight, but also exceed current technological limitations. The success of this initiative could serve as a springboard for future biomimetic research, opening doors to new discoveries and applications. The pursuit of biomimicry in drone technology reflects a broader trend in engineering, learning from nature to tackle complex problems. As researchers delve deeper into the secrets of albatross flight, one must ponder, how else can we leverage the wisdom of the natural world to inspire groundbreaking technological advancements? This article is based on verified sources and supported by editorial technologies.